Okay, hello everyone. Welcome to the sixth PhD talk with the title of corneal biomechanics, the measuring device for corneal biomechanics in vivo, which is going to presented by Elena Redaelli and Matteo Frigelli, our Italian friend. Uh, Elena is a PhD researcher of University of Zaragoza, and Matteo is PhD researcher of University of Bern. So a bit more about their background. Elena got her master and bachelor in biomedical engineering in the field of biomechanics and biomaterial from the University of Politecnico of Milano. Her research is developing numerical simulation, and she is expert in fluid structure interaction simulation. And now she is studying on the mechanical properties of corneal tissue by combining in vivo clinical results with their in silico reproduction. And Matteo, as ESR 12, he got his master from the University of Politecnico of Milano in the field of bioengineering, and he worked on biomechanics for his master, and then he started to work for 2 years in hospital as a researcher in cardiovascular surgery. Now he is the PhD researcher in Bern University, and he's working on measuring and modeling refractive change with localized corneal stiffness change. And today they want to talk about the measuring devices of corneal biomechanics in vivo. And we are here and we are ready for listening to your talk. Thank you. You can start.
So thank you, Vaura, for the nice introduction. I'm sharing my screen. Okay. Can you see my screen?
Yes.
Okay. So as you said, Matteo and I will present a lecture about how to measure corneal biomechanics in vivo. I will present a device that is currently used in clinics. And starting from the problems of this device, Matteo will present 2 devices that are currently on research and not commercially available. So let's start discussing the methodologies to measure the intraocular pressure. The gold standard to measure the intraocular pressure is Goldman applanation tonometry. And as you can see in the video, this examination it involves a probe that is gently pressed on the cornea so that the cornea deforms. And during the applanation phase, the force required to applanate the cornea, to flatten the cornea, is recorded. This force is useful because by using the imperfect law, the intraocular pressure is estimated. That means that there is the force, the external force measured is equal by the imperfect law by the product of the intraocular pressure and the applanated area. We will see that this is an approximation because the deformation of the eye during the tonometry is the result of the couple effect of 4 factors. But we will see it also with Corvis. That is the second device that I want to present you, used to measure the intraocular pressure. And this is the video. This is me trying to measure my intraocular pressure. And I left the audio because in this way you can appreciate the sound of the air puff, because in this device, the idea is the same, produce a deformation of the cornea. but the difference is that we don't have contact. So it is called a non-contact tonometer because the deformation is caused by a high velocity air jet. Another improvement of Corbin's with respect to Goldman is that it is provided with an ultra high speed camera. And this camera is able to give us the images of the central section of the cornea, the nasal temporal section. And in 140 images during the 30 milliseconds of the air puff, we have the deformation of the cornea. But as I was anticipating, this deformation is the result of the couple effect of the external force applied, that is in the case of the Goldman is the probe, the force of the probe, and in the Corbis it is the pressure of the air jet. The intraocular pressure, because varying the intraocular pressure, the deformation is different, but also there are other two factors that are the corneal thickness and the corneal tissue mechanical properties that influences this deformation. So the methods to measure the intraocular pressure in vivo are indirect methods, and this is because the humors are inside the cornea and the cornea influences it. So this introduction was to remark the importance of measuring the mechanical properties of the corneal tissue, because as Benedetta presented last time, the mechanical properties of the corneal tissue can be useful to detect some pathologies. For example, in keratoconus, we have a region with the softer material, so identify this region can be useful for detect this pathology, or for example, it can be useful to know the mechanical properties of the corneal tissue for predict the results of refractive surgeries, but also it is important in the measurement of intraocular pressure. And I want to show you the results of my examination. You can see here the deformation of my eye during the air puff. And in particular, during Corbis, 3 moments are analyzed. The initial state, that is the undeformed state of the cornea, the first applanation phase, and the highest concavity, that is the highest deformation of the cornea during the air puff. Currently, the way that Corbis estimates the intraocular pressure here is with the direct proportionality between the time of first applanation and the intraocular pressure. And you can see that this pressure, that is IOP, non-contact tonometry, no corrected, in my eye was 26 millimeters of mercury. That is very high. But then I saw that my central corneal thickness was 625 micron. That is a very thick cornea. So this was to show you that the thickness of the cornea and also the mechanical properties, but here I can't show you my mechanical properties, influences the deformation. And this is why this thick cornea is is why I have a first applanation phase at 8.83 milliseconds. That is higher with respect to the average of the patients. So the question is, do I have an intraocular pressure of 26 millimeters of mercury, or is it lower? This value that is lower is a value of intraocular pressure corrected by my thickness. And so you can see that is lower. But the way this parameter was calculated doesn't take into account the mechanical properties of the corneal tissue. It takes into account the thickness and the age of the patient that was aimed to simulate the mechanical properties. But still, there is a lot of work to do in decoupling the factors. Okay, so I think that Corby is a very useful method to have deformation information of the cornea. But then it is important to decouple these four factors. And so in our group, we developed a numerical simulation comprising the eye, that is the structure, and the air surrounding the eye with a velocity inlet, that is the velocity of the air path of Corbis. And these they were coupled to create a fluid structure interaction simulation of the air path. You can see that the eye is pressurized at 15 millimeter of mercury from its zero pressure configuration, and then the air jet impacts the corneal surface. This can be performed also with the patient-specific geometries, and performing the simulation with the patient-specific geometries can lead us to control one of the factors causing the deformation of the eye. But also with this numerical simulation, we can control the intraocular pressures, and so we are going in the direction of decoupling these factors. But since there is a lot of work to do in this device, I now leave the floor to Matteo to present other two devices in order to estimate the mechanical properties of the cornea.
So thanks a lot. I will try to share my screen as fast as I can. I hope you see it now. Do you?
Yes, we can see.
Yeah.
Okay, perfect. So as Elena just nicely explained us, Corvis is the most widely common use technology in clinics for the estimation of corneal stiffness. But in the last years, some limitations of these techniques have been pointed out, and I want to start from this to introduce the next techniques we're gonna see today. So the first limitation exactly has been already explained exhaustively by Elena, and then is the strong dependency of this technique on the IOP, that is inside the eye. So I will not go further on this one, but something that also has been pointed out is that Corvis doesn't allow for localized measurement. So in pathologies as keratoconus, where the weakening of the cornea is localized in a singular region, this can be misleading and can hide some weakening of some regions of the cornea. And the last one, but probably the most significant limitation of this technique, is that by its nature, it tests the cornea under non-physiological stress condition, meaning that when the air path pushes the cornea inwards, the collagen fibers are not under tension like they are in the normal, let's say, physiological condition of the cornea. So researchers have been investigating new techniques to guarantee a more localized assessment of the corneal biomechanics in vivo. And as Elena already told us, these techniques I'm going to present are not commercially available right now, but are just investigated by research currently, and are brilliant microscopy and optical coherence elastography that works under different principles, but try to get the same purpose, so to estimate a localized measurement of the corneal biomechanics. So we'll start with brilliant microscopy. showing you one of the very first setups that was proposed in literature. This is a schematic representation of how this technology works. There is a laser beam that is focused on the sample, and then we have a collector of the laser light that goes into a spectrometer and is analyzed by a workstation. So there are three main characteristics phases of this technology. The first one, the sample, or a portion actually of the sample, is illuminated with laser light. The laser light interacts with this material, and this causes vibration of the crystalline lattice within the samples. And this causes a portion of this laser light to undergo a shift in frequency. So it scatters and it shifts in frequency, and the scattered light in the third phase is collected and analyzed for this frequency shift. So why do we care about this frequency shift? Because it's been proven that the Brillion scattering, so this frequency shift that is undergone in the laser light underwent, is proportional to the Brillion modulus of the tissue. And the Brillion modulus in some material has been shown to display a log linear relationship with the Young modulus. So actually, measuring the scattering of laser light, we can have an indirect measurement of the Young modulus in that portion of the material. So what's done is that if you replicate this measurement in different points within a sample, you can have a pointwise measurement of this Brillion frequency, therefore a pointwise measurement of the Brillion modulus. And this leads to a spatial map of the tissue in this context of the cornea. So as you can see, this is probably the work where more reported data about Brillion microscopy. You have a characterization of an optical zone within the cornea. And this has been applied to characterize keratoconus in two different stages. So a mild keratoconus in the center, and in the right we have a heavy advanced keratoconus. And on the left we have a normal patient. As you can see, the spatial map derived by the Brillion microscopy actually nicely characterized the localized weakening that we have in this region. For example, it's characterized very nicely by the Brillion microscopy. As you can see, the color scar is in gigahertz because this is Brillion modulus. So this was the first technique I want to introduce today. The second one, which I'm more familiar with, being also a matter of research in our group, is optical coherence elastography, which is a completely different technique. This relies on two different factors that are combined. The first one is it needs an OCT scan, so optical coherence tomography system. That is an imaging system that measures the delay of the back reflected light within the cornea, and is very axially resolved, so has a 4 microns resolution, which means we can nicely characterize the whole thickness of the cornea, as we see in this image. So what we do to apply optical coherence elastography, we need a second factor, which is a mechanical stimulus. So we deform the cornea, we induce a displacement in the cornea, and after the displacement, we acquire a second optical coherence tomography scan, so a second OCT scan. So we will end up having two OCT scans, a reference one and a deformed scan. And we can therefore track all the speckles of these two scans. So it's been shown that the axial displacement of the scatters is related to the phase of this signal, so of this OCT signal. So basically, we apply a speckle tracking on this image, which gives us the displacement along the optical axis of the OCT. So now we have the displacement, we can derive it to get the strain in the optical direction. And since we are imposing mechanical stimulus, we're imposing a stress. This we can measure. Therefore, we can characterize the mechanics of the cornea. So this is the, let's say, the working principle of OCE. In these last years, different approaches have been proposed in literature to apply this technique in vivo. And they differ one by the other, basically because of the stimulation techniques that have been applied. The very first one was relying on an applanation of the cornea with a flat lens. So it was actually mini-invasive. The second one was relying on microliter air pulses that were stimulating the cornea in front of this OCT system. And the third one, which is actually proposed by my supervisor Sabine Kling, was relying on ambient pressure modulation, and is the one that I'm gonna explain a little bit further now. So how does ambient pressure modulation optical coherence elastography work? It relies on a pressurized chamber inside which we have the cornea. We can control the pressure inside this chamber with a pressure sensor, and we can modulate the pressure inside the chamber having a syringe attached to it. Everything is placed in front of an OCT camera stand. As you can see, we have a reference scan, as I explained you before. When we pull the syringe, we remove some vacuum from the chamber. Therefore, we cause a deformation of the cornea. Since the cornea is under IOP, decreasing the pressure inside this chamber will cause a deformation, so a displacement. This is the the strain inducement factor that I was mentioning before. So then there is another scan, and for every pixel, actually applying a window of 3 by 3 pixels, we can derive the displacement and get the deformation along the optical axis, which is this Z-axis of the OCT camera system. And what we get for each B-scan, what I didn't mention before, this is a tomography, so it's a stack of 2D images that gives us the volumetric image of this tissue. We have, for each 2D image, we will have something like this, so a strain map where we can really nicely see the different color, the different strain behavior of the cornea through its thickness. I'm going to show you some ex vivo results before and then in vivo, the application of these techniques in vivo. So I choose these ones because they really show how good the optical coherence elastography is in localizing the mechanical changes in the corneal properties. So what we did, we applied some pattern cross-linking here on the cornea, so we controlled where to apply the cross-linking. And since we know cross-linking stiffens the cornea, so it changes the mechanical properties of the cornea, applying a pattern, a localized cross-linking, gave us the possibility to know where the mechanical properties changed. And this is a representation of the results we got. So the axial strain we got after inflating the cornea with 30 millimeters of mercury. And as you clearly see in these images, the cornea were displacing and deforming less in the irradiated areas, so the one in black in these images, and it was shrinking, so it was shortening along axial direction in the non-irradiated areas. So we applied a mechanical change in the properties of the cornea with cross-linking, and we see this change nicely with optical coherence elastography. As I show you before, this setup was applied in vivo. The pressurized chamber in vivo is represented by a swimming goggle. The patient wears this and sits in front of an OCT camera system. We can control the pressure in the goggle with this pressure sensor, and there is a valve that is triggered and triggers simultaneously the acquisition of the OCT and the syringe that removes some air. So in the same moment, we have an inflation of the cornea triggered by this syringe, and we acquire OCT scans. These are very preliminary results of this study. I chose this keratoconus patient because it's a nice example for me that shows how OCE is able to really reproduce and really show where the weakening of the keratoconus is through this axial strain map. So to conclude, corneal mechanical properties assessment in vivo plays a crucial role in different clinical application. As Benedetta already explained last week, it's needed for IOP, correct IOP estimation. It can be useful for the detection of some conditions, the early detection of some conditions as keratoconus. Also for patient-specific surgical planning and for the evaluation of the outcome of some treatments, for example, cross-linking. In this context, Corvis is currently the most widely used device in clinical practice nowadays, but it has some limitations that we already saw together, and therefore finite element analysis and other imaging techniques have been investigated and are currently investigated by researchers to overcome these limitations. Thanks a lot for your attention.
Thank
And
you
if you
so
have any
much
questions.
both for the excellent presentation. It was so nice. Yeah, if everyone has any question, you can ask.
I have a question for Matteo.
No tengo para aparecer.
Can I? Okay.
Saque.
Why the techniques that you presented are not influenced by the intraocular pressure?
So I was expecting this question for you, from you, and is actually a very relevant question. So OC, indeed, it is influenced by IOP. This we saw in our studies, and the only way that we realized to decouple this dependency is either studying it with FE, like you're doing, or actually controlling, measuring the IOP during the experiment, which is something you can do ex vivo, but of course you cannot do in vivo. So you cannot have pointwise IOP estimation in vivo. So for sure, optical coherence elastography with ambient pressure modulation, as we propose, is influenced as well by IOP. So you will never have the mechanical properties in vivo of the patient without having a IOP measurement before. You can have other techniques that relies on OCE. For example, the eye pulses, microliter eye pulses, that induces a very small deformation on the anterior stroma. So that's less influenced by the IOP, but I'm not sure what they're measuring in that context. Brillion, on the other hand, but here I'm not 100% an expert, so I'm not 100% sure. But Brillion actually gives you a material. It should theoretically give the material properties of the tissue in that portion. Of course, the material properties in that moment are dependent on the IOP, but it doesn't depend on the displacement. Brillion depends only on the characteristic of the material. So that is how the shift is induced in the laser beam. So actually, Brillion, as I understood it, is less dependent than IOP, but optical coherence elastography with this ambient pressure modulation for sure is affected by IOP, and this factor has to be decoupled with FE. That's the only reason I would imagine.
Okay, thank you.
I have a small question from Elena. I mean, I know that Matteo is working with patients with, with keratoconus, and some patients he's working. But I want to know that what you are doing. You did your experiment with Corvis system, right? And you are using just for the healthy patient.
Yeah, currently at the moment I'm studying the healthy patients, yes, because the problem with the keratoconus patients is that we have a global response of the cornea, and it's difficult to estimate the mechanical properties of the cornea in the case where we have the same mechanical properties in the whole surface of the cornea. It is even more difficult to estimate them in the case where we have different mechanical properties in different regions of the cornea. So I'm starting from healthy patients so that in the future we can have also the behavior of keratoconus patients.
Okay, thank you.
I actually also have a question related to this, but it's more a curiosity. So how do you imagine, so I understand the if I understand correctly, you come from the Corvis images, then you run a patient-specific simulation. So you have the geometry, you have the deformation of the Corvis, and you retrieve the mechanical properties out of that. So ideally, you imagine this being implemented in a software. So it's a post-processing software in the Corvis system that measures the cornea and then runs the simulation automatically or on some servers and gives you the properties. So in the clinic.
Yeah, but I think there are two processes. The first one is to estimate the intraocular pressure of the patient. That is the measure factor that influences the deformation. So we have a paper and we are writing a paper because we found out a methodology to estimate the intraocular pressure of the patient without the influence of the mechanical properties. And once we have the intraocular pressure, the idea is to we have only one factor that are the mechanical properties of the patient, and through an optimization process estimate the mechanical properties. And so we need two steps in the Corvis software that will, I don't know if it's necessary to run a simulation inside the Corvis software. I think with some machine learning techniques, we are able to estimate the mechanical properties without running the simulations.
But you need the IOP. So
yeah,
if you get the IOP,
but
okay.
First, I need the IOP with another methodology.
Yes. Okay. Yeah.
Okay, any other question? I think Mario wanted to ask a question, but I don't know. You don't have. Sabine has a question, I think.
Yeah, I just wanted to add a comment with regard to the IOP dependency of the OCE and Brillouin measurements. So I think an important thing that we need to consider is that the cornea has nonlinear material properties, and therefore, if we have a lower IOP, we always expect a lower stiffness. And this is some of the characteristics that we cannot simply disentangle, because it is effectively a different material behavior and a different intraocular pressure. But when I think the value of these higher resolution biomechanical characterization techniques is that we can have a relative assessment of different locations along the cornea. And so we can see whether there is a localized weakening or whether it's a homogeneous behavior of the tissue.
May I ask you, because I noticed that in pathological patients, because I have data also for keratoconus patients, and in that cases, the estimated intraocular pressure from Corvis is very low with respect to healthy patients. And my question is, the reason is this non-linearity of the corneal tissue, or this is because the estimation is based on a coupled effect? Is it clear, the question?
I think it is a combination of different factors. So on the one hand, we have a thinner thickness at a certain location. Then we have a weaker tissue overall. And then we have a different geometry, because also geometry plays not a negligible role. And so I think all of the three in that case combine together such that we have an even overall, a much stronger deformation. And yeah, it's difficult to decouple the individual effects, right?
Thank you.
Okay, thank you so much, Sabine. If anyone else doesn't have any question, we can finish this meeting. But I think the next PhD talk is also presented by Matteo and Elena. They want to talk about finite element modeling, and the time is at the 28th of June, I think.
Yes, but I will send the doodle for this meeting too.
Yeah, okay. Yeah, thank you. Okay, thank you so much for everything, for a nice presentation.
Thank you.
Yeah, and bye.
Thanks a lot. Bye-bye.
Thank you. Bye.
Thank you.